Hi, let's take a look at AP Review 9 today. AP Review 9. Problem number 1 says consider the differential equation dy dx equals x to the fourth y minus 2. And the first thing they ask us to do here is to make a slope field. With 12 points. Okay, so I start with y equal to 2 because the slope will be 0 there. So 0 slope, 0 slope, 0 slope. And if x equals 0, then I also have a 0 slope. So here's x equals 0, and I have a 0 slope here. That's not so bad. I've only got 6 points to find. If I put in x equal to 1 and y equal to 0, I get negative 2. If I put x equal to 1 and y equal to 1, I get negative 1. And if I put x equal to 1 and y equal to 3, I get positive 1. Now what about negative 1? If I plug in a negative 1, that's still positive. Negative 1, 0, that's the same slope, that's the same slope, and that's the same slope. Okay, so there's part A. And part B. While the slope field in part A drawn as only 12 points, it is defined at every point on the xy plane. Describe all the points in the xy plane for which the slopes are negative. So I wonder when dy dx is dy dx, the slopes are negative. dy dx is less than 0. Well, let's find some critical points. We know that well, just from what I'm looking at here, I kind of want to say I have this critical value, y equals 2, and if I plug a 2 in, because this is always going to be positive, there's nothing that will make that negative. So I'm only looking at this piece here, and if I plug in numbers to the left of 2, like 0, I get a negative, and if I plug in numbers bigger than 2, then this is a positive times that positive that's already there. So I want to say dy dx is less than 0 for y less than 2. Y less than 2. Okay, so there's part B, there's part A, and what about part C? Part C would be find the particular solution with f of 0 equals 0. Okay, so let's solve this. We know that they want to see separation of variables. So we've got dy over y minus 2 equals x to the fourth dx. We integrate both sides. We get ln absolute y minus 2 equals x to the fifth over 5 plus c. We exponentiate, and we get y minus 2 equals plus and minus e to the c, e to the x to the fifth over 5. And let's say plus and minus e to the c equals b. So we've got y equals 2. All right, I'll do it in 2 steps. Y minus 2 equals b, e to the x to the fifth over 5, or y equals 2 plus b, e to the x to the fifth over 5. Okay, now let's plug in our initial condition, 0, 0. So I've got 0 equals 2 plus b to the e to the 0 is 1. And so I get b equals negative 2. And so our f of x equation, our particular solution, is 2 minus 2 e to the x to the fifth over 5. Okay, so there's part C. Don't forget to show the separation of variables. That's terribly, terribly important. Don't forget to show this little guy here. And don't forget to use your initial condition and show that you're using the initial condition. Okay, problem number 2. 2 says consider the differential equation dy dx equals y minus 1 over x squared. So we get dy over y minus 1. Oh, I'm doing a particular solution. This is part B. Okay, well, I'm going to finish part B now. Equals 1 over x squared dx. Okay, so I need to integrate both sides. This is ln of y minus 1, and this is negative 1 x to the minus 1, or negative 1 over x, plus c. And then we exponentiate, and we get y minus 1 equals plus and minus e to the c, e to the minus 1 over x. Let's say plus and minus e to the c equals b. So y minus 1 equals b e to the minus 1 over x. What initial condition do they give us? They give us 2, 0. So I get negative 1 equals b e to the negative 1 half, which is the same as negative 1 equals b over square root of e. So I get that b equals negative root e. So then our particular solution, f of x, would be 1 minus square root of e times e to the minus 1 over x. Or, because this is the same base, they'd probably write this as e to the 1 half minus 1 over x equals f of x. That's my thought on what the f of x would be in this case. Yep. And now what about the slope field for part A? Slope field for part A. 1, 2, 3 up, and 4 across. And we've got this. So if I plug in y equal to 1, I get a 0 slope. Except when x equals 0, then I have 0 over 0. In fact, when I plug in x equals 0, I have these undefined slopes. And this one is 0 over 0, so without L'Hopital's rule, I feel reluctant to do something with it. But maybe I'll think about that as we go a little further. If y equals 0, I have a negative 1 on top, and let's plug that x value in and square it. So 1 over negative 1 over 1 squared is negative 1. And negative 1 over 2 squared is negative 1/4. And if I plug in a negative 1 for x, well, the same thing happens. Y equals 0, so I have negative 1 on top. I square the negative, and I get this. What about 1, 2? 2 minus 1 is positive 1, and so I end up with this slope. And if I plug in negative 1, 2, I get the same slope. And if I plug in 2, 2, I've got 1 on top and 4 on the bottom, and so I have a slope of 1/4. Okay, so there's my slope field. And then it says here, hey, what's the limit of f of x as x heads to infinity? So if I know that f of x equals 1 minus e to the 1 half minus 1 over x, and I plug an infinity over there, 1 over infinity is 1 pizza, infinite people, that's 0 pizza for you. So this is what I get. I get 1 minus e to the 1 half, or 1 minus square root of e. That's part C. Okay. Yeah, so what about that point? Well, the limit here, the value here was 0 over 0. So if I use L'Hopital's rule, oh no, it's implicit. I would have dy dx over 2x. Okay, so we want to evaluate that at the point 0, comma 1. So here's dy dx, and if I put in 0, lo and behold, I'm sorry, 0 comma x equals 0, y equals 1, yes. I still get infinity over infinity. So I'm not going to be able to evaluate this. I don't think. Well, so let's replace. So that's y minus 1 over x squared. And then I flip and multiply, and that gives me y minus 1 over 2x to the third. Yes, I still get that 0 over 0 situation. The denominator keeps getting bigger. So that's, no. How about we'll call it undefined, if you really want to put something there. Okay, problem number 3. Let's take a look at problem number 3. I think there's a good chance that you're going to see a problem like this on the AP exam, because College Board spent the last week putting up videos all about solving differential equations on their YouTube live channel. And it seems like, why would they do that if it wasn't part of the tested material? Okay. 3. Now consider dy dx equals x plus 1 over y. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15. Okay, so what can we say? When x is negative 1, we have a 0 slope. And when y is 0, we're undefined. Oh, y is 0. We're undefined slope. Ooh, what about here? Negative 1, comma 0. We have an undefined slope. Okay, so let's find these 4 and these 4. If I make y equal to 1, that's just whatever I get here divided by 1. So I've got 1 plus 1 is 2 over 1 is 2. And here I have 0 plus 1, 1 over 1 is 1. And then if I put in 0, 2, 0, 2, I get 1 half. And if I put in 1, 2, 1, no, 1, 2, I get 2 over 2 or 1. So these should be parallel. If I put in 0, negative 1, the negative 1 on the bottom, 1, negative 1 is negative 1. If I put in 1, negative 1, 1, negative 1 is negative 2. If I put in 0, negative 2, I get 1 over negative 2. And if I put in 1, negative 2, I get 2 over negative 2, which is negative 1 again. So that's what my slope field looks like. Yep. Okay, and now that's part A. Part B, when the slope field in A is drawn to the 12 points, defined at every point, describe all the points for which dy dx equals negative 1. Well, I saw this negative 1 slope here. And negative 1 slope happened when I know it's here. Can I go back to that one? No. I guess I want to say when, what's the equation of that line? Well, oh, I know. When the slope was negative 1, when negative y equaled x plus 1. So that's y equals negative x minus 1. Anywhere along this point for x values, I think greater than, let's see, if we plug in a negative 1 here, we get 0, negative 1. If we plug in a negative 1 here, we get 0. So what? Negative 1, 0 is 0 over 0. So I can't go back to here. How about there if I plug in a negative 1/2? Negative 1/2. Negative 1/2 is 1/2. Y equals net. Yes. So I want to say for x greater than negative 1. I wonder if it continues back here. Oh, maybe it's only this point. Maybe that's it. Let's check. So if I plug in a negative 2 and a 1, negative 2 and a 1. Ooh, that's also a slope of negative 1. So it's not a restriction on x's, it's a restriction on y's. Y can't be 0. Okay. All right, so this is the set of all points where the slope of our function will be negative 1 whenever y is equal to this version of x. And the only place that doesn't work is at y equal to 0. And now let's take a look at part C, which is probably the solve the differential equation part. Find the particular solution given that f of 0 equals negative 2. Okay, so we've got dy dx equals x plus 1 over y. Y dy equals x plus 1 dx. Let's integrate both sides. Y squared over 2, x squared over 2 plus x plus c. I'm going to multiply every place by 2. Y squared equals x squared plus 2x plus 2c. I'm going to plug in my initial condition now. I get 0, negative 2. Negative 2 squared is 4, 0, 0, 2c, c equals 2. So if I take c equals 2 and plug it in there, and yeah, you really want to show negative 2 equals 0 plus 0 plus 2c, c equals 2. So y equals plus and minus square root x squared plus 2x plus 4. Okay, now let's take a look at our particular solution. When we have our particular solution, we're supposed to get a negative 2 when we plug in 0. Well, if I plug in zeros here, I get 0 plus 4 is 4. Square root of 4 is 2. At plus and minus 2 equals negative 2. So it's not plus or minus, it's just minus. There's our particular solution, part C for number 3. Okay, let's take a look at number 4. Number 4 says dy dx equals x squared y minus 1. Part A says fill in the slope field. 1, 2, 3, 4. Okay. Whenever y equals 1, I have a slope of 0. Whenever x equals 0, I have a slope of 0. So if I put in 1, 0, a 1 over here and a 0 for here, I get a slope of negative 1. If I plug in a negative 1 and a 0, I still get negative 1, because this is always positive. If I plug in a slope of 2, I've got 1 times 1 is positive 1. Same thing at negative 1. And if I plug in 3, I've got 2 times 1 is 2. And this will also be 2. Okay, there's my slope field, part A. Part B says Slope drawn 12 points to find everywhere. Where are the slopes positive? Well, regardless of what x value I plug in, the slopes would always be positive. The only thing restricting the positiveness of my slopes is my y value. So let's take this y value of 1 and plug in some numbers on either side. If we plug in a 0, I get a negative times a positive is a negative. And if I plug in a 2, 2 minus 1 is positive times positive is positive. I've got dy dx is less than, greater than 0 or less than 0. Slopes are positive. Greater than 0 for y greater than 1. There's my answer to part B. Part C. Find the particular solution given the differential equation and f of 0 equals 3. Okay, so let's make a little room here. We've got dy over y minus 1 equals x squared dx. And then we integrate both sides, and we've got ln y minus 1 equals x to the third over 3 plus c. We exponentiate. We get absolute y minus 1 equals e to the x to the third over 3 plus c. Make sure that c is up there in the exponent. Oops. Now I'm going to get rid of that absolute value and have plus and minus e to the c times e to the x to the third over 3. Let's say plus and minus e to the c equals b, and we can say y minus 1 equals b e to the x to the third over 3. And if we plug in that initial condition, remember they told us f of 0 is equal to 3. 3 minus 1 is 2, and e to the 0 is 1, so b equals 2. And so then my particular solution is going to be y equals 1 plus 2e to the x to the third over 3. Plus or minus e to the c equals b. Good, so there's our particular solution, 1 plus 2 times e to the x to the third over 3. Excellent. There's number 4. Let's take a look at 5. 5. We're told that dy dx equals y plus 1 over x. And this time we're given 1, 2, 3, 4, 5. And there's that. We've got this one, this one, this one, this one, this one, this one. And wings, and then down here. Okay, so when y equals negative 1, I have a 0 slope. When x equals 0, we're undefined. And if I plug in 1, 0, I get 1 over 1, which is 1. If I plug in 1, 1, I get 2 over 1, which is 2. If I plug in 2, 0, 2 here and a 0 here, I get 1 half. Now what happens when I plug in negatives? If I plug in negative 1, 0, I get a slope of negative 1. If I plug in negative 1, 2, I have 3, negative 3. Did I have 3 here? Oh, that's not 2, that's 1. So 2, negative 2. And then if I plug in a negative 2, 0, I have negative 1 half. Okay, there's my slope field. And part B says find the particular solution. Well, this only has B parts when f of negative 1 equals 1. Okay, so we've got dy over y plus 1 equals 1 over x dx. and we integrate both sides, we get ln of y plus 1 equals ln of x plus c. We exponentiate, and we get y plus 1 equals e to the c times e to the ln of absolute x. So I've got y plus 1 equals plus and minus e to the c, e to the ln of absolute x. Let's say that plus and minus e to the c equals b. And so now I've got y plus 1 equals b. And e to the ln, they undo each other. They definitely undo each other. So I end up with absolute x here. Okay, now let's plug in the initial condition. So we've got 1 plus 1 equals b times absolute negative 1. B equals 2. And so our specific solution, don't forget to subtract this 1. Y equals negative 1 plus 2 absolute x. Okay. That's a little unexpected. Oh, that's the specific solution through that ordered pair. I understand now. And state its domain. Ooh, state its domain. Well, can't I plug any number in there? Domain is all real numbers. But wait a minute. Is that true? Negative 1, 1. That's this line here. Well, I have an undefined, so that's just the pointy point. Yeah, I kind of like all real numbers there. I have a note here that says that you could also do y equals negative 2x minus 1 for x less than 0. But why can't I use x greater than 0 also? Yeah, that's, I guess that I only concern myself with the part that contains that point, and x greater than 0 would be the other half of the piecewise function. Ew, I don't like that. I feel dirty. Okay. Problem number 6. dy dx equals negative xy squared over 2. Part A, draw the slope field. Point, 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 point. Okay, let's take a look. If we plug in x equal to 0, we get a 0 slope. That's these. If we plug in y equal to 0, we get a 0 slope, and that's those. If we plug in the point 1, 1, we have negative 1/2. If we plug in the point 1, 2, 1, 2, this would be negative 4 over 2, or negative 2. If we plug in the point 2, 1, we have negative 2 over 2, which is negative 1. And if we plug in 2, 2, we've got 4 times 2, 8, negative 8 over 2, which is negative 4. Okay, and then over here, if we plug in negative 1, 1, we get positive 1/2. And negative 1, 2, we get positive 2. Is it positive 2? 4? Yes. Okay, so there's part A. Part B for number 6. Write the equation of the line tangent to f at -1. Well, we know f of -1 equals 2. They tell us that in the stem of the problem. And then I need f prime of -1. So don't I need an ordered pair? Yes, I do. So I plug in -1 there, and I get -1, 2 squared over 2, which is that positive 2 that we had before. And so y minus 2 equals 2x plus 1. Or if you needed to take this further, y equals 2x plus 4. That would be my tangent line equation, but I would stop here. Okay, and then part C says find the particular solution through that point. So let's solve this differential equation. I've got dy over y squared equals -x dx. And don't forget that 2. We integrate. Remember, not everything in a denominator is an ln. This is going to be -1 over y equals -x squared over 4 plus c. We've got this to find. I think I want to multiply everything by negative. So I'm going to have 1 over y equals x squared over 4 minus c. And now I'll plug in the ordered pair, -1, 2. So I've got 1 over 2 equals 1/4 minus c. So I subtract 1/4 from both sides. I get 1/4 equals -c, or c equals -1/4. So I can come back up here and write 1 over y equals x squared over 4 minus 1/4. And I think I'm going to do 1 over y equals x squared minus 1 over 4. And then I'm going to flip both sides and say that y equals to 4 over x squared minus 1. You could always multiply both sides by 4, multiply both sides by 1, divide both sides by this stuff, and you'd end up in the same place. Here's our particular f of x solution. This is the end of part C. Okay, problem number 7. Says, consider this differential equation. Dy dx equals y minus 1 squared cosine pi x. Part A, sketch the slope field. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so if we plug in y equal to 1, we have a slope of 0. If we plug in, I don't know, so 1 is cosine equal to 0, at pi over 2. So only at 1/2 would I have that 0 slope. So let's just plug in and see what we get. Okay, if I plug in 1, 0, I get 1 times, I plugged in a 1 here. Cosine of pi is -1, I have a slope of -1. If I plug in 0, 0, cosine of 0 is +1. I plugged in a 0 here, and I still got 1, and so I've got a slope of 1. Oh, that's interesting. If I plug in a -1, I've got -pi, which is -1 again, and I'm back this way. It's sort of cosine-y, isn't it? Okay, now what about plugging in 1, -1? So that's going to be -2 squared, which is 4. And if I plug in a 1 here, cosine of pi is -1, I get a -4. If I plug in 0, -1, well, this is still going to be 4. Plugging in a 0 here gives me cosine of 0 is +1. So I have a +4 slope, not to be confused with the +1 slope. And then this one will be the same as that one because of the periodicity of cosine. So there's part A. Part B for number 7. Horizontal line with the equation y equals c satisfies the differential equation. Find the value of c. Find the value of c. Well, I see that here. This is a slope, a horizontal slope. So y equals 1. So c must equal 1 is my answer. For y equals to have a horizontal tangent or slope of 0 everywhere. Okay, part C. Part C says solve the differential equation, find the particular solution. We've got dy dx equals y minus 1 squared cosine pi x. So dy over y minus 1 squared equals cosine pi x dx. And then I integrate both sides. Remember, not everything on the bottom is an ln. This is -1 over y minus 1. And over here, the antiderivative of cosine is going to be sine of pi x. But don't forget, if you took the derivative of this, there'd be a times pi out in front. There's no pi here, so there must be an over pi plus c. Okay, so what was our initial condition? Our initial condition was f of 1 equals 0. If I plug in 0 over here, I get -1 over -1, which is 1. If I plug in a 1 over here, sine of pi is 0 plus c, so c equals 1. So now I've got -1 over y minus 1 equals sine pi x over pi plus 1. Ew, look at that. And I'm supposed to solve this equation for y equals. So let's be careful about that. Yes, let's be careful about that. Okay, first thing I'm going to do is I'm going to multiply everything by -1. So I've got 1 y minus 1, 1 over pi, sine pi x, and don't forget that's a negative now, minus 1. And I'm not gonna do that first. All right, I'm gonna do that first. Now over here, I'm gonna make a common denominator. I'm gonna multiply by pi over pi so that I can write this as y minus 1 equals negative sine pi x minus pi over pi. And then I'm going to flip both sides, and I'm going to have y minus 1 equals pi over negative sine pi x minus pi, and I'm going to add 1. So pi negative sine pi x minus pi plus 1. Ew. That's the thing. And that's it. Yeah. Okay. I mean, I guess you could pull that negative onto the top, but you're not going to be able to cancel those. And you can't pull this off and make it -1 plus 1. That's not going to work either. This is our f of x. And that's why you're getting the 6 points for that. Ugh. Okay, there's problem number 7. Let's take a look at problem number 8. Problem number 8. Ooh, not slope field. Very interesting. Function models skateboard ramp meets the following conditions. X of 0, the value of the function is 0, and the slope of the function is 0. So x of 0 equals 0, and x prime of 0 equals 0. Okay, at x, oh, this is the function. Okay, f prime of 0 equals 0. And then they tell me that at x equals 4, the value of the function is 1, and the slope at 4 equals 1. And then between 0 and 4, f is increasing, so f prime greater than 0 on 0 to 4. Actually, they said between, not including. So this is all my given information as I go to look at answering these questions. Part A says, what if f of x equals ax squared? For a equals a non-zero constant, show that it is not possible to find a value of a that meets requirement 2 above. So we can't meet that requirement. Okay, so if f of 4 equals 1, then we know 1 equals a 4 squared, a equals 1 over 16. In which case, f would be 1 over 16x squared, and then f prime would be 1 over 8x. Well, if this meets little double I, then this should also be true. 1 equals 1/8 times 4. 1 equals 1/2. Nope. Not possible. Not possible. Okay, there's part A. What about part B? Part B says, what about g of x? G of x equals cx to the third minus x squared over 16. And in this situation, they say c is not 0, find c, so that we do meet the requirements for little double I. Okay, so 1 equals 64c minus 4 squared is 16 over 16 is 1. So I get 2 over 64, or 1 over 32 equals c. So then g of x would be 1 over 32 x to the third minus x squared over 16. Let's plug in let's plug in 4 for x and 1 for the slope into the derivative. So g prime equals 3 over 32 x squared minus 2x over 16. Okay, and if we plug in 4 here and 1 here, we've got 1 equals 3 over 32 times 16 minus 8 over 16. So I get 1 equals 48 over 32 minus 1/2. This is 3/2, and I get 1 equals 1. So we meet condition double I with this g of x, with this c value. Okay. Part C. Part C, using your function, show that it does not meet the requirement for triple I. It's this requirement. So is f prime greater than 0 on 0 to 4 for this function? for this function. So I want the derivative, and I want to find when the derivative is equal to 0. I'm going to pull out an x over 16 to make my life a little easier. I'm going to have 3 halves x minus 2. Okay, I'll set each of these equal to 0. I'll get x equals 0, that's fine. And then I'll have x equals 3x over 2 equals 2. 3x equals 4. X equals 4/3. Ooh, 4/3. That's on our interval. If I make an f prime sign chart with 0 and 4/3 and test 1 and 2 in here, in G prime, if I plug in a 1, I get 3 over 32 minus 4 over 32 is negative. Well, since G prime is less than 0 on 0 to 4/3, g of x does not fulfill triple I. Okay, that's part C, and now finally part D. Part D says, let h of x be x to the n over k, where k is a non-zero constant and n is a positive integer. Find values of k and n so that we meet requirement 2, 1, and 3. Okay, so let's start. If we plug in 4, we should have 1 equals 4 to the n over k, or k equals 4 to the n. Now, if I have the derivative of this function, h prime will be n x to the n minus 1 over k. If we plug in our 4, 1 here, we get 1 equals n times 4 to the n minus 1 over k, or k equals n times 4 to the n minus 1. Well, I know what k equals, so I can say 4 to the n equals n times 4 to the n minus 1. Do I like that? I think I like that. I'm a little scared about that. Let's see where I can go with that. So I set them equal to each other, and how about we divide both sides? Yeah. Let's divide both sides by 4 to the n minus 1. 4 to the n minus 1. And the reason I want to do that is because when the bases are the same and I'm dividing, I can subtract the exponents. So I'm going to have 4 to the n minus 1 equals n, or 4 to the n minus n plus 1 equals n. And that's 4 to the 1 equals n, or n equals 4. And now that I know what n equals, I can come back up here and say that k equals 4 to the 4th, or 256. Okay, so then we say that our equation is h of x is x to the 4th over 256. Well, let's see if then that's what meets requirement 2. Let's see if we meet requirement 1. Do I plug in a 0 and get a 0? H of 0 equals 0. Yes. H prime is 4x to the 3rd over 256. Is h prime of 0 equal to 0? Yes, it is. So we met condition I as well. Now, what about this derivative? Um, so I've got 4x to the third over 256, and I want this to be, this has a critical value at 0. If we plug in a negative, we get negative. If we plug in positive, we get positive. And sure enough, h prime is greater than 0 for x greater than 0. So condition 3 is met. All right, so we met all the conditions with this function here. H of x equals x to the fourth over 256. With problems like this, don't get freaked out. Just, take it one step at a time. Okay, so, blah, blah, blah. Problem number 9, our last problem, says y equals x to the n. Tangent line at 1, 1. So we know that this passes through 1, 1. And what else? Where n is greater than 1. Okay. Find the integral from 0 to 1 of x to the n dx in terms of n. Well, the antiderivative would be x to the n plus 1 over n plus 1 from 0 to 1. And remember, these are x values. There should be n's in our answer. If I plug in a 1, I get 1 to the n plus 1 over n plus 1 minus, if I plug in a 0, 0 to this power is going to be 1 over n plus 1. Okay, so 9a. Oh. If I factor out, no, oh, if I factor out a 1 over n plus 1 here, I'm going to have 1 to the n plus 1 minus 1 to the 1. This is 1 times 1 to the n minus 1, which is 1 to the n minus 1. So I have 1 to the n minus 1 over n plus 1. Is that tidier? Oh. Excuse me. I feel like I'm missing something. My notes say that this integral is equal to 1 over n plus 1. But when I evaluate from 0 to 1, 1 to the n plus 1 is this over this, and if I plug in a 0, I get 0 to the stuff, which is 1. I think I just didn't complete the evaluating. Okay, so I'd go with either this one or this one for 9a, but I'm going to look that up just to be sure. Oh, it was a long time ago. Okay, so maybe we won't see a problem like this. Part B. Tangent line at x equals 1. Let the triangular region bounded by the tangent line at x equals 1. Okay, so this, and this, I guess it's That's my tangent line. And they're saying that this area, t equals 1 over 2m. All right, well, let's see what we need to do this. I kind of want to find this area by finding the area of this triangle. So I know that's 1/2 base times height. I know the height here is 1. Well, that's convenient. And so I just need to find out how long this base is. Well, I know that this distance is 1. From here to here is 1. So this distance then has to be something less than 1. Can we find the x-intercept of the tangent line? Okay, so what do we know about the tangent line? The tangent line passes through the point 1, 1. And what do we know about the slope of that tangent line? Y prime equals nx to the n minus 1. Yes? Yes. And if I want y prime of 1, I've got n times 1 to the n minus 1. Okay. So what would my tangent line equation be? My tangent line equation would be y minus 1 equals n times 1 to the n minus 1 times x minus 1. And if I want to find a y-intercept, I set y equal to 0, and I'm solving for x. Now, let's see if we can tidy this up. 1 to the n minus 1 is the same as 1 to the n over 1 to the 1. So that's just 1 to the n. So I've got n times 1 to the n for x minus 1 equals negative 1. Now, I know that n is always greater than 0, and so this will never be negative, so I won't have any 1-overs here. This n is always positive, so I'm always going to have just a positive 1 here. Oh, that's nice. That's always positive 1. So then I add 1 to both sides, and I get x equals 0. That's not true. The tangent line isn't at 0. Orf. All right. That's not working. Huh. Well, let's think about this some more. I'm looking for a mistake. Why is that negative 1? Oh, that's negative 1 because it's y minus 1. Okay, and I plugged in y equal to 0 to find the x-intercept. Okay. Excuse me. My eyes are acting up just at the wrong time. So, B. Okay. Oh, that's still n. Duh. Okay, that's better. And now I set y equal to 0, and I solve. and I get nx minus n equals -1, nx equals n minus 1, x equals n minus 1 over n. Aha, I have an x value now. This x value is n minus 1 over n. Okay, so let's see what we can do then. We know that this x value is 1, and so this base will be 1 minus n minus 1 over n, which is 1 minus, I'm going to split this into two fractions, n over n minus 1 over n, which is going to give me 1 minus n over n plus 1 over n, and that's what base is, which is 1 minus 1 plus 1 over n, or 1 over n. So base is 1 over n, so we've got 1/2 1 over n times 1, or 1 over 2n. That's the area of T. Great. Okay. And now, what about part C? Let S be the region bounded by the curve and the tangent line and the x-axis. Express the area of S in terms of n, and determine the value of n that maximizes S. Okay, so here's our S region, and I think that this is the area under the curve, and this is our triangle, and if we do the area under the curve from 0 to, oh god, where was that place again? N minus 1 over n, and subtract, oh no, let's just go 0 to 1, and subtract from that the area of T, we should get area S. Okay, so let's see what we get here. This integral, which we already did in part A, minus that area. So that's x to the n plus 1 over n plus 1 from 0 to 1 over 1 over 2n. And I had notes saying that this was 1 over n plus 1. Wow, I really need to go back and figure out why that is, because here it is in my notes again, minus 1 over 2n. That's area of S. So if I want the area of S prime, I need to take the derivative of each of these. So that's n plus 1 to the minus 1 minus 2n to the minus 1. Actually, I would feel better about that. So I take the derivative and I get -1 over n plus 1 squared minus plus 1 over 2n squared. I'm going to make a common denominator here. And I'm going to have -2n squared plus n plus 1 squared all over 2n squared n plus 1 squared. That's S prime, area of S prime. Combining like terms, well, -2n squared plus n squared plus 2n plus 1 over 2n squared n plus 1 squared. So I've got -n squared plus 2n plus 1 over 2n squared n plus 1. If I factor a negative out, -n squared minus 2n minus 1, and that's not going to factor. So I have to use quadratic formula. Oh, lucky me. So n equals negative b, negative 2 plus or minus square root of b squared minus 4ac all over 2a. So I got negative 2 plus or minus square root of 8 over negative 2. Okay. This is an exciting algebra experience. N equals negative 2 plus 2 root 2 over negative 2, negative 2 minus 2 root 2 over negative 2. So here, 2 plus 2 root 2, I can actually take out a negative 2. 2 plus root 2 over negative 2. These will cancel, and I get this value for n. But over here, if I try that same thing, I get, I took out a 2, so that's a 1. If I take out a negative 2, I get 1 minus root 2 over negative 2. Now, root 2 is bigger than root 1, so this is going to be a negative number. But we were told at the beginning of the problem that n is positive. So I discard this solution, and I only have 1 plus root 2. Okay, so let's plug in 1 plus root 2. We'll plug in a 1, and this is going to be 2.4, so we'll plug in a 3 into our n prime. 1. I get a positive on top. That's going to be a positive. That's going to be a positive, so I get a positive. If I plug in a 3, I have negative 9 plus 6 plus 1, which is negative, and I still have positive on the bottom, so that's a minus. So we've got a max area at 1 plus root 2. All right, 1 plus root 2. That looks great. Now, I really feel like I need, and do we have to justify? No, it just says find the value. So this, when n equals 1 plus root 2, area of S is maximized. All right, but I want to go back to part A. I mean, if you're all set, then you're all set. But I want to go back to part A and say the integral of x to the n from 0 to 1 dx. I know from my notes that this is supposed to be that, but I wasn't getting that before. So let's see if I can figure that out. X to the n plus 1 over n plus 1 evaluated from 0 to 1. Again, these are x values. I'm plugging these in for x. So I've got 1 to the n plus 1 over n plus 1 minus, if I plug in a 0 here, I have 0 to a power, which is 0. There we go. And so now I have this part, which is 1 to the 1 times 1 to the n over n plus 1, which is 1 because n is bigger than 0. Yes, I hear you, not infinity. I get 1 over n plus 1. Okay, so on the interval from 0 to 1, I'm getting this as my value of that integral. So then when it comes time to do the integral from 0 to 1 of x to the n dx minus the area of t, this makes sense to me now that that's 1 over x plus 1 minus 1 over 2n. There's my area of S. There's my area of S function, and that's the thing that we took the derivative of to find the maximum of S. Okay, that's AP9. I hope that was helpful for you. Boy, solving those differential equation problems went pretty fast. The last two, very algebra heavy. Those were from 2006 and 2004, so I'm not sure that you'll see that, but you could. It's certainly fair game. Have a great day, everyone.